derivative of f inverse at x equal 1 over derivative of f at f inverse of x. So we don't try to memorize a formula. We try to memorize the way we can recover the formula for derivative of f inverse. We just get started with the following identity. F of f inverse of x equal x for n x of the domain of f inverse. And then we just evaluate x side of this equation with respect to x. So here we get derivative of f inverse at x equal 1 over derivative of f at f inverse of x. So here, look at this formula. To get derivative of f inverse at x, we have to find f inverse of x. Here, you have got f. You can evaluate derivative of f easily. The key thing here is you have to determine f inverse of x. Okay, now let me give you an example. I say another slide. Wait. Okay, can you see the new slide?
Yes.
Okay. Now we consider the function f given by x to the fifth plus 2x cubed plus 7x plus 1. Now find the derivative of f inverse at 1. So here, f is one-to-one function. Why? I explain it later. Okay? Why f is one-to-one function? I explain it later. The key thing here is the main question here is how to get the derivative of f inverse at 1. So we just apply the above formula, right? Here you see, I just write down again the above formula in which x is just 1. Here you see, derivative of f inverse at 1 equal 1 over derivative of f at f inverse of 1. So you have got the function f, it's just a polynomial. You can evaluate f prime of x easily. Here, f prime of x of course give you 5x to the 4 plus 6x squared plus 7. Like this, huh? Here. It's so easy, huh? F prime of x equal 5x to the 4 plus x squared plus 7. It's easy. The key thing here is you have to determine the values of f inverse of 1. Where to find f inverse of 1? How to find f inverse of 1? We just apply the definition of inverse function. Suppose that f inverse of 1 equal a. Then by definition of inverse function, it's equivalent to f of a equal 1. Here, f of a equal 1. What does it mean? It means we have to find a number a, so that's f of a equal 1. F inverse of 1 equal a. It means that's f of a equal 1. So what is the number a here? I just replace x with a. And it's equal 1. So here you see, it gives you a equals 0. Clearly, when a equals 0, you see f of a give you 1, right? It means f inverse of 1 equals 0. And that's why now you have got derivative of f inverse at 1 equal 1 over f prime of 0. You got f prime of x already. You can evaluate f prime of 0 easily. Just replace x with 0, you have got 7. So f inverse of 1 equal 1 over 7. The key thing here is we have to determine f inverse of 1. And then how to get f inverse of 1? Suppose that f inverse of 1 equal a. Then by definition, f of a equal 1. And as you can see here, clearly when a equals 0, you have got f of a equal 1, right? Some student may ask me the following question. Maybe we have got another value for a. For example, when a equal 100, maybe f of 100 equal 1. It is impossible. You know why? Because f here is a one-to-one function. For x value of f, you have got only one value, f of x. And conversely, for x value of y, you have got only one value of x, so that's f of x equal y. So 0 here is a unique number, so that's f of 0 equal 1. Because f here is a one-to-one function. Now we go back the question. Why? Why f is one-to-one function? You know why? Why f is one-to-one function? Look at the function f. Why f here is a one-to-one function? Who give me the answer of the questions? Mai Phương?
No.
No. Okay. Phụng?
Chắc sử dụng definition hả thầy?
No.
No.
Aha. Okay. Now I give you the answer for this question. What is the derivative of the function f? Now look. F prime of x gives you 5x to the 4 plus 6x squared plus 7, right? It means that f prime of x always positive, right? Exactly here, f prime of x always greater than or equal to 7, right? And what does it mean? It means the function f is strictly increasing. Strictly increasing. All right? And that's why here f is one-to-one function. Strictly increasing function is one-to-one function. Okay? Yeah. So a strictly increasing function is one-to-one function. Because if you have got x1, x2, you see? Now let me explain a little bit more here. Okay. All right. Maybe we use this. So here you see, why f is one-to-one function? Here you have got f of 0 equal 1, right? And f is increasing. So when x greater than 0, you have got f of x greater than 1, right? And when x less than 0, you have got f of x less than 1. And that's why there exists a unique number. It's just 0. So that's f of 0 equal 1. When x greater than 0, f of x greater than 1. When x less than 0, f of x less than 1. And that's why 0 here is a unique number. So that's f of 0 equal 1. One-to-one function. Okay? So just keep in mind that if the function f is strictly increasing, and if the function f is differentiable, is equivalent to f prime of x positive, then f is one-to-one function. And that's why 0 here is a unique number. So that's f of 0 equal 1. Okay? All clear, guys?
Yes, yes.
You got it, Phương?
Yes.
Okay. All right, one more example. Now, I say another slide. Wait. One-to-one function. Okay. Can you see the new example, Phương? Phung?
Yes, yes.
Okay, now
Yes.
look. Once again, here you have got a polynomial. And now the question here is find the equation of the tangent line to the graph of f inverse. To the graph of f inverse at the point 4, 1. Okay. The tangent line to the graph of f inverse, not f, okay? To the graph of f inverse at the point 4, 1. So, first of all, we show that P, the point with coordinates 4, 1, belong to the graph of f inverse. I mean here, f inverse of 4 equal 1. Or is equivalent to f of 1 equal 4. You can check it easily. If you replace f with 1, f of 1 give you number 4, right? Here, I do it for you already. When you replace f with 1, you have got f of 1 equal 4, right? 1 minus 2 plus 3 plus 2, huh? Okay. Number 6 minus 2 give you 4. So f of 1 equal 4. And that's why f inverse of 4 equal 1. It means P here belongs to the graph of f inverse, right? And that's why the equation of the tangent line to the graph of f inverse at the point P given by just y minus 1 equal derivative of f inverse at 4 pi x minus 4. Derivative of f inverse at 4 give you the slope of the tangent line to the graph of f inverse at P. You remember? So all we have to do here is we just find derivative of f inverse at 4. Now, here, similarly at the above example, now we find derivative of f inverse at 4. And we use the formula for derivative of f inverse. Derivative of f inverse at 4 equal 1 over derivative of f at f inverse of 4. And f inverse of 4 here equal 1, huh? Because f of 1 equal 4. So all we have to do here is we evaluate f prime of 1. Derivative of f at 1 is so easy. It gives you number 2. So derivative of f inverse at 4 gives you 1 over 2. And that's why you get the equation of the tangent line to the graph of f inverse at P. Okay. Just y equal 1 over 2x minus 1, huh? All clear, guys? All clear?
Thầy ơi cho em hỏi một cái nữa, ý là đối với cái dạng bài này á, thì ban đầu mình có cần phải luôn luôn phải chứng minh cái function fx nó là one to one function không thầy?
Nếu mà người ta cho cái hàm đó có nghĩa là one to one function. Còn nếu mà người ta yêu cầu chứng minh thì mình phải chứng minh. If the question is so that f is one to one function, you have to prove it. Right? You have to show it. Here, the question here is right. Find the equation of tangent line. It means f is one to one function. And we assume that f is one to one function already. Okay?
Okay.
Yeah. All right, now we go to the main slide. Let me say another slide. Can you see a new slide, Phong?
Yes.
Now we discuss derivative of inverse trigonometric function. All right, so here you see we can prove the following formula for derivative of inverse trigonometric function. For example, derivative of sine inverse of x equal 1 over square root of 1 minus x squared for any x between -1 and 1. Derivative of cosine inverse of x equal -1 over square root of 1 minus x squared. Here x is between -1 and 1, and so on. The question here is how to prove the formula, how to prove the identities. Okay, so it follows from derivative of inverse function. Now, for example, we try to prove the first identity. Here, we give the fruit of the first identity. Now, y equal sine inverse of x is equivalent to sine of y equal x. Sine of y equal x. Okay? Here, y is between minus pi over 2 and pi over 2. Why? Because if we consider x as a function of y, and y is between minus pi over 2, pi over 2, x is 1-to-1 function. Okay? Yeah. Here, y is between minus pi over 2, pi over 2. Because if we consider the function x equals sine of y, this function is 1-to-1 function. If y varies from minus pi over 2, pi over 2. Now, we differentiate each term of the second equation with respect to x. I mean, we differentiate each term of the equation sine of y equal x. Keep in mind that here, y is a function of x. And that's why here we apply the chain rule. Okay? Keep in mind that y is a function of x. So, we go from the left to the right. First, we meet the function sine. Derivative of sine gives you cosine. Cosine of what? Cosine of the inner function. It means cosine of y. And then times derivative of the function y. Here I write dy by dx. The derivative of x, of course, gives you what? Or we have got dy by dx equal 1 over cosine of y. It means the derivative of the function sine inverse of x now given by 1 over cosine of y. Keep in mind that y here is between minus pi over 2, pi over 2. So cosine of y always non-negative. It's clear, huh? And that's why we use the following identity. Cosine of y equal square root of 1 minus sine of y squared. Normally you have got plus minus cosine of y equal plus minus square root of 1 minus sine of y squared. However, here y is between minus pi over 2, pi over 2. So cosine of 1 always non-negative. 1-to-1 function. Remember, it means square root of 1 minus x squared. And that's why we get dy by dx equal 1 over square root of 1 minus x squared. It means the derivative of sine inverse of x equal 1 over square root of 1 minus x squared. It follows from the general formula for derivative of inverse function. And we just use the definition of inverse function here. You see, the fruit is very, very elementary. In the same way, you can show that derivative of cosine inverse of x equal minus 1 over square root of 1 minus x squared. Derivative of tan inverse of x give you 1 over 1 plus x squared and so on. Okay? Yeah. We consider this example already. I omit. Okay. Now we go to a new technique for differentiation, namely logarithmic differentiation. Sometimes we have to evaluate derivative of a function which involve loss of exponents and multiplication. For example, you see, look at the function y of x given in the example. Y of x equal x plus 1 square times x plus 2 square and so on. You see, we have got loss of exponents and multiplication. Of course, you can use the product rule, you can use quotient rule, and we get derivative of the function y. However, you have to calculate a loss of thing, right? Okay. Here, we can apply a new technique for differentiation. Logarithmic differentiation. Now, I give you an example. Here, you see. To evaluate the derivative of the function y given by x plus 1 square, x plus 2 square, and times x plus 4 cube, all divided by the product x minus 1 times x plus 5. First, we take logarithm both sides of the above equation, and you have got natural log of y equal natural log of the quotient on the right hand side. Okay, and now using properties of logarithmic function, we can rewrite this equation like natural log of y equal to natural log of x plus 1 plus 2 natural log of x plus 2 and so on. Just use some basic properties of logarithmic function. Okay, now next we differentiate each term of this equation with respect to x. Okay, on the left hand side, keep in mind that y here is a function of x. So derivative of natural log of y with respect to x gives you 1 over y times y prime. On the right hand side is so easy, huh? Derivative of 2 natural log of x plus 1 give you 2 over x plus 1 and so on. It's so easy. And that's why here you have got y prime equal y times 2 over x plus 1 plus 2 over x plus 2 and so on. You see? And you get the derivative of the function y easily, very quickly. Okay? Yeah. So the key thing here is, first we take logarithm both sides of the function y, and using some basic properties of logarithmic function, we can rewrite the right hand side as the sum of 2 natural log of x plus 1, 2 natural log of x plus 2, and so on. You see? And then we evaluate the derivative of each term of this equation with respect to x. Now, one more example. Now we want to find the derivative of the function g given by 4 root of x squared plus 1 over x squared minus 1. Of course, here you can apply the chain rule and quotient rule. You get derivative of the function g. Here we apply logarithmic differentiation technique. So we take logarithm both sides of the function y, and you have got natural log of y equal, all right, natural log of 4 root of x squared plus 1 over x squared minus 1. And using basic properties of logarithmic function, you have got 1 over 4 times natural log of x squared plus 1 minus natural log of x squared minus 1. Now we differentiate each term of this equation with respect to x. At the above, derivative of left-hand side give you y prime over y. Keep in mind that y here is a function of x, so we apply the chain rule here. Okay. All right. Derivative of the right-hand side is easy, huh? We can get it easily. We apply the chain rule here. 1 over x squared plus 1 times derivative of x squared plus 1 is mean 2x. Similarly, you have got derivative of the function x squared minus 1. So y prime give you y times 1 over 4 2x over x squared plus 1 minus 2x over x squared minus 1. And you get derivative of the function g easily. Huh? This technique is called logarithmic differentiation. Now, what is how to get the derivative of the function x to the x? How to get the derivative of the function x to the x? Here x is a positive number. So you see here, x to the x is not a power function. I mean, it is not a function of the following form. Let me write down something here. Power function is mean x to the alpha. Something like x squared, x cubed, and so on. In general, x to the alpha is called a power function. A power function requires that the exponent must be constant. 2, 3, maybe 1 over 2, and so on. Okay, and it's not exponential function. I mean, it is not a function of the form a to the x. Exponential function. Okay, here exponential function requires that a here must be a constant. Moreover, a is a positive number. Yeah. Here you have got x to the x. It's not a power function. Okay? It's not a power function. It's not an exponential function. And that's why you cannot apply the formula for derivative of power function or derivative of exponential function. So how to evaluate the derivative of the function x to the x? We use the logarithmic differentiation method. We take logarithm both sides of the equation. Y of x equal x to the x. And it gives you natural log of y equal natural log of x to the x. And it gives you x times natural log of x. Now differentiate both sides of the last equation. We get y prime over y equal derivative of the right hand side. Okay, just apply product rule, huh? Natural log of x plus 1. So y prime equal y times natural log of x plus 1. This means x to the x times natural log of x plus 1. Similarly, you can evaluate the derivative of the function psi of x to the x. Here x is between 0 and pi. Okay, because psi of x should be positive. And in general, we can use the methods of logarithmic differentiation to evaluate the derivative of a function of the form u of x raised to the quantity v of x. Okay? Yeah. All clear here? All clear, guys?
Yes, yes. So teacher, we use this technique for all the function that is so complicated, like the power or the product. We convert them into plus and more and multiply. Is it right?
Yeah. When you have got a function that involves loss of exponents and multiplication. Here you see, look again this function. You have got a loss of exponential. Okay? You have got a loss of multiplication. X plus 1 square times x plus 2 square times x plus 4 cubes over x minus 1 times x plus 5. Okay, yeah. You can apply, of course, you can apply the quotient rule, the product rule to evaluate derivative of the function y. I mean product rule, quotient rule for differentiation. However, you have to calculate a loss of 10, huh? Logarithmic differentiation technique give us a very, very nice way to get derivative of a function that involve loss of exponents and multiplication. Okay, and especially it allows us to get derivative of the function of the form u of x raised to the quantity v of x. All right. All right, linear approximation. Okay, maybe read yourself, huh? Read it yourself. And maybe you learn it again when you go up to years maybe in numerical analysis, huh? Okay. Okay, yeah. Okay, now let me tell you a little bit about linear approximation. Yeah. Okay, wait a moment. I want to tell you a little bit about linear approximation. Wait a moment, please. All right. So let me tell you a little bit about linear approximation. The main idea here is you have got a function f, and now you want to get an approximation of the function f by a linear function. Here you see, suppose that you have got a function f, right? Okay, f is a function of f. Now we want to find a linear function. It means the function of the form y equal ax plus b. All right. And f of x is approximately by the linear function ax plus b in a neighborhood of a given number. I mean f of x is approximately by, I do something, huh? Approximately by ax plus b in a neighborhood of a given number. Okay. So here, look at the figure. We have got the graph of the function f. It's just the blue curve here. Okay. Now we consider the point with coordinate a at a. It belongs to the graph of f, right? And suppose that at this point you have got the tangent line to the graph of f. You see? And now when x close to a, you see the curve, I mean the graph of the function y equal f of x and the tangent line look like the same. What does it mean? It means when x close to a, the value of f of x very, very close to the values of the tangent line. And that's why here we use the equation of the tangent line at a at a linear approximation of the function f at the point a at a. So roughly speaking here, the equation of the tangent line, as you can see here on the right hand side, f of a plus f prime of a times x minus a, y equal f of a plus f prime of a times x minus a is exactly the equation of the tangent line to the graph of f at the point a at a. And when x close to a, the value of f of x is approximately by fa plus f prime of a times x minus a. It means when x close to a, we can approximate the value of f of x with the values of the tangent line to the graph of f at the point a fa when x close to a. This is called the linear approximation of a given function. So here you see, look again the figure you see here. When x close to a, you see the graph of f and the right line look like the same, right? Here, by definition, the approximation, the function f is approximately by fa plus f prime of a times x minus a is called the linear approximation or tangent line approximation of the function f at a. And the function f of a plus f prime of a times x minus a, exactly the equation of the tangent line, is called a linearization of the function f at a. So here, let me give you an example. We want to find the linearization of the function f of x given by square root of x plus 3 at 1, a here equal 1. And then we use to approximate the number square root of 3.98 and square root of 4.05. So first of all, we can approximate the function f by a linear function at a. It just the linear function here is just the equation of the tangent line to the graph of f at the point 1 and 2. Here you see when a equal 1, it means when x equal 1, f of 1 give you number 2, right? So here f of 1 equal 2. Now, to find the equation of the tangent line to the graph of f at the point 1, 2, we have to evaluate derivative of the function f at 1. It means the slope of tangent line to the graph of f at the point 1, 2. So here we evaluate f prime of x. It's so easy, right? And you have got f prime of 1, give you just 1 over 4. Okay. And that's why the equation of the tangent line is just y equal to plus 1 over 4 times x minus 1. It gives you here just 7 over 4 and plus x over 4. And now the function f of x is approximately by the linear function L of x equal x over 4 plus 7 over 4. Here just a linear function. It means a function of the form ax plus b. And we get the following linear approximation. Square root of x plus 3 is approximately by x over 4 plus 7 over 4. Now we can use this approximation to approximate the number square root of 3.98 and square root of 4.05. Here, you see. All right, so here, why you guys are here? For example, the first approximation, why you have got here square root of 3.98 is just 1.995. How to get this approximation? Okay, here, square root of 3.98. You can rewrite like this now. Okay, I write out here for you. Square root of 3.98. You can write like this now. Okay, equal now square root of 3 plus 0.98. It's clear, huh? And 0.98 here stands for x. And by the above approximation, square root of 3.98 is approximately by 7 over 4 plus 0.98 over 4. Similarly, we get the second approximation. Of course, now you can rewrite 4.05 at 3 plus 1.05. And using the above approximation, we get 2.0125. Okay? Yeah. All right. All right. Now, I want to tell you a very, very important concept in differentiation of function of one variable. From the above linear approximation, you see here, give you a function f, you can find a linear approximation of the function f at a given number a. F of x here is approximately by the linear function f of a plus f prime of a times x minus a. Okay. So here, from equation number 3, you have got f of x minus f of a. Okay, f of x minus f of a e approximately by f prime of a times x minus a. You just remove f of a on the left hand side. You have got f of x minus f of a e approximately by f prime of a times x minus a. And if we call delta x is just x minus a, and delta y is just f of x minus f of a. From equation number 3, we get delta y is approximately by the product f prime of a times delta x. It means the change in y is approximately by derivative of the function f at a times the change in f. All right. In mathematics, the product of f prime of a times delta x equals the differential of the function f at a. It's just product of f prime of a and delta x. And in general, we replace number a with an arbitrary number x0. You have got the differential of the function f is defined by f prime of a times delta x. And in particular, when f of x equal x, you have got differential of f e also dx and is equal delta x, because f prime of x now equal 1 for every x, right? And that's why in general, instead of using delta x, we use dx. And the product f prime of a times dx equal the differential of the function f at a. So dy given by f prime of a times dx equal the differential of the function f at a. Differential. Now look at the figure, you see. We suppose that the graph of f given by the blue curve here, you see, the red line stands for the tangent line to the graph of f at the point P with coordinates x, f of x, okay? Yeah. All right. So here dx equal delta x is just the change in x. All right. Delta y here is just the change in y. So what is dy? Differential of the function y at x. As you can see here, dy represents the amount that the tangent line changes, rise or falls. So dy here gives you the amount that the tangent line changes, rise or fall. Okay? The concept differential of a function of one variable is very important. We use it in differential equation. Okay? And it has some basic properties. Something like we have got the following properties of differential of function of one variable. These of f plus g equal df plus dg. And these of lambda, okay, maybe a times f equal A pi df. And these are f over g equal g df minus f dg over g squared. It follows from the definition. All right, maybe we when you learn differential equation, you encounter again the concept differential. Just keep in mind that dy represent the amount that tangent line rise or falls. It means the tangent line change. You see, the change of tangent line. Here, x change from x to x plus delta x, and dy give you the amount that the tangent line changes, rise or falls. And by definition, just keep in mind that dy given by f prime of x dx for any number x. Okay. All right, wait a moment. I want to show you another slide here. Wait, please. All right, can you see the new slide, guys?
Dạ thấy thầy.
All right. Now we go to application of differentiation. Now you have got enough technique for differentiation. So we go to application. And we have got several basic problems here. Related rate problem, extreme value, mean value theorem, and so on. Okay. All right. First of all, I want to discuss again the problem finding a maximum value, minimum value of a function of one variable. Now, wait. Yeah, it's here, huh? All right. Now, we go back the problem, finding the maximum value and minimum value of a given function. The question here is when there a function f has an absolute maximum and an absolute minimum, And you remember in the previous chapter, you learned it already. If the function f is continuous on a closed interval AB, you remember, then the function f attains a maximum value and a minimum value on this interval. You remember this theorem? You learned it in the previous chapter. If the function f continuous on a closed interval AB, then f attains the maximum value and minimum value on the interval AB. It means that f takes on both an absolute minimum and an absolute maximum value on the closed interval AB. It's quite easy to understand it. If the function f continues on a closed interval AB, so the graph of the function f on this interval should have a highest point and should have a lowest point. The highest point on the graph gives you the maximum value of the function f on the closed interval AB. The lowest point on the graph of f gives you the minimum value of the function f on the closed interval AB. The question now is how to find the absolute value, minimum, and absolute maximum value of the function f on the closed interval AB. In the previous chapter, we just know that if the function f is continuous on a closed interval AB, then f had a maximum value, minimum value on the given interval. However, we do not know how to get them. Okay, now you should learn how to find the maximum value and minimum value of a function f on a closed interval AB. Here, just remind you the definition of maximum value, minimum value. Okay. Actually, here we have got a flexible concept: local maximum and local minimum value of a given function. So here, the function f has a local minimum at a number c if f of c less than or equal to f of x for all x near c. What does it mean? It means that this is a neighborhood of c. C minus delta, c plus delta, so that f of c is the minimum value of the function f on this interval, c minus delta, c plus delta. For all x near c, it means that f of c is the minimum value of the function f in a neighborhood of c. I mean that this is a number delta positive. So here c minus delta, c plus delta stand for a neighborhood of c. And f of c is the minimum value of the function f on this interval. Local minimum. It's just a minimum value of the function f on this interval only. Okay? Local minimum value. Similarly, if the function f has a local maximum at c, by definition, the function f is said to have a local maximum or relative maximum at c if there exists a number delta, so that f of c is the maximum value of f on the interval c minus delta, c plus delta. It means that this is a neighborhood of c, so that f of c is the maximum value of the function f on this neighborhood of c. It also means f of c greater than or equal to f of x for all x near C. Local maximum. The function f is said to have a local maximum at C if f of C is the maximum value of the function f on some neighborhoods of C. On some neighborhoods of C. It means that this number delta here of course a positive number, so that f of C is the maximum value of the function f on the interval C minus delta, C plus delta. Now, look at the following figure you see. So here you have got f of 1 equal 5, right? F of 1 equal 5. The point with coordinates 1, 5 belong to the graph of f. F of 1 equal 5. So number 5 here, f of 1 equal 5, and number 5 here is a local maximum of f. You see here, when x close to 1, you see the point 1, 5 give you the highest point on the graph of f. When x close to 1 only. Similarly, here you have got f of 3 equal minus 20, minus 27. It gives you a local minimum of f. And in this case, it also an absolute minimum of f. All right. Now we go to a very, very important theorem. Very, very important properties of maximum value, minimum value of a function. Here, this theorem says that if the function f has a local maximum or a local minimum at C, and f prime of C at this, then f prime of C must be 0. What does it mean? It means if the function f has a local maximum or local minimum at C, and at the point C, FC, the graph of f has a tangent line, then the tangent line to the graph of f at that point must parallel to the x-axis. You see, f prime of C equals 0. It means that the tangent line to the graph of f at the point C, FC is parallel to the x-axis, right? So here, if the function f had a local maximum or local minimum at C, and f prime of C at this, then f prime of C equals 0. It means the tangent line to the graph of f at the point C, FC must parallel to the x-axis. Okay? This theorem gives you a necessary condition so that the function f attain a local maximum or a local minimum at a number C. A necessary condition for which the function f attain a local maximum or local minimum at C. Just a necessary condition. Now look at the figure you see here. The function f had a local maximum at C, and it had a local minimum at D. And at the point C, FC or D, FD, you see here the tangent line to the graph of f at C, FC or D, FD is parallel to the x-axis. You see? How to prove it? You see, the proof is very, very elementary, very, very easy. I show you right now. Okay, here. We discussed a little bit about the proof of this theorem. It's called the Fermat theorem. Now, for example, we suppose that f of c is a local maximum of f. What does it mean? It means that this a number delta positive, and f of c is the maximum value of the function f on the interval c minus delta, c plus delta. You see here, c belongs to the interval c minus delta, c plus delta. C belongs to the open interval c minus delta, c plus delta. It's very important. So here, the function f attains a local maximum at c. It means that this number delta is a positive number. So that f of c is the maximum value of the function f on the interval c minus delta, c plus delta. It also means you have got f of c greater than or equal to f of x for any x of the interval c minus delta, c plus delta. F of c is the maximum value of the function f on this interval. Okay? Yeah. And now we have got one more assumption here. We assume that f prime of c at this. So f prime of c at this, the function f is differentiable at c. It also means f prime of c at this. And you remember it's equivalent to the right derivative of the function f and the left derivative of the function f at c, both at this, and they are equal. I mean the right derivative of the function f at c equal the left derivative of the function f at c. And of course, it's equal f prime of c. Now, you see, so here, f prime of c equal the right derivative of the function f at c and equal the left derivative of the function f at c. Now, f prime of c equal the right derivative of the function f at c. By definition, the right derivative of the function f at c gives you the limit of the different quotient at x minus fc over x minus c when x approaches c from the right. X approaches c from the right. X approaches c from the right means x greater than c. So x minus c always positive, right? Moreover, f of x minus f of c less than or equal to 0 because f of c is the maximum value of the function f on the interval c minus delta, c plus delta. So when x close to c, f of x minus f of c less than or equal to 0. And that's why the quotient f of x minus f of c over x minus c negative or equal 0 when x close to c. And that's why the limit of this quotient when x approaches c from the right gives you a negative number or 0 number. On the other hand, f prime of c equal the left derivative of the function f at c, and by definition, it's just the limit of the different quotient f of x minus f of c over x minus c. Now x approaches c from the left. It means x approaches c and x less than c. So x less than c, so x minus c always negative. In this quotient, x minus c negative because x approaches c and x less than c. F of x minus f of c always negative or equal 0. And that's why now this quotient, I mean f of x minus f of c over x minus c, when x approaches c from the left always positive or equal 0. And that's why it limit non-negative. So here, f prime of c non-positive and f of c non-negative. I mean f prime of c less than or equal to 0 and f prime of c greater than or equal to 0. That's why it must be 0. In this proof, you say the number c must belong to the interval c minus delta, c plus delta for some positive number delta. It also means f of c here is a local maximum or local minimum. If f of c is a local minimum of f, the proof is very, very similar of what we did here. So in summary, now you see, if the function f had a local maximum or local minimum at c, and f prime of c at this, then f prime of c must be 0. And that's why now, when we find a maximum value and a minimum value of a function f, we pay our attention to some number c at which either f prime at c does not exist or f prime of c equals 0. All right, let me remind you again. By the Fermat theorem, here and later on, when we find the maximum value or minimum value of a given function f, we pay our attention at number c at which either f prime of c does not exist or f prime of c at this and equals 0. Here you see. The above theorem only offer a necessary condition. It's not a sufficient condition. In Vietnamese, it's just điều kiện cần. Alright, but not sufficient condition. Không phải là điều kiện đủ. Here is a counter example. You see, we consider the function y of x equal x cubed. Clearly, you have got f prime of 0 equals 0, right? Because f prime of x gives you 3x squared. So when you replace x with 0, you have got f prime of 0 equals 0. However, f of 0 gives you 0, right? However, 0 here is not a local maximum. It's not a local maximum. I mean, the function f had no local maximum, no local minimum at the origin. The above theorem gives us just a necessary condition. If then, okay. One more example here, you see, f of x equal absolute value of x, And here is the graph of the function absolute value of f, you see? And f prime of 0 does not exist. We proved it already. Okay? However, the function f here attains a local minimum at 0. Exactly, here's the absolute minimum value of the function f. The above theorem gives us just a necessary condition. If the function f attains a maximum value or minimum value at c, and f prime of c at this, then f prime of c equals 0. But f prime of c equals 0 does not ensure that the function f attains a maximum value or minimum value at c. A implies B. So B here is just necessary condition for A. B here is just necessary condition for A. B does not imply A. A implies B. Okay? All right, maybe have break, huh? Right time for break. So, have break.
Có gì thầy gửi cái file slide này lên
Of
trên
course,
box.
don't worry. Okay. I offer the lecture right now. Don't worry, huh? And get back at let me see. Okay, 3 o'clock, huh? Okay, I offer the PDF file of my lecture right now. I will upload the file in the chat box. Don't worry. All right, I uploaded the file for you already in the chat box. Have you got a phone?
Yes, I got it.
All right. Have practice. All right, get back to class, please. Can you hear me?
Yes.
Yes.
All right. So, as I mentioned above, if the function f attain a maximum value or minimum value at a number c, then either f prime of c equals 0 or f prime of c do not exist. Okay? And such a number is called a critical number of the function f. And when we find a maximum value or minimum value of a given function, we pay our attention to critical number. So, first of all, by definition, a critical number of a function f is a real number in the domain of f. This number must belong to the domain of f. And either f prime of c equals 0 if f prime of c exists, or f prime of c does not exist. So here, by definition, c must belong to the domain of f. And either f prime of c equals 0 or f prime of c does not exist. Now we consider some example. Find critical number of the following function f of x given by x to the 3 over 5 times 4 minus x. So we just apply product rule. Product rule for differentiation. We evaluate f prime of x. As you can see here, f prime of x give you 12 minus ax over 5 x to the 2 over 5. So f prime of x equals 0 when x equals 3 over 2. We find all number x so that f prime of x equals 0. Moreover, we find a number x so that f prime of x does not exist. Here you see f prime of x gives you 12 minus ax over 5 x to the 2 over 5. So this quotient is undefined when x equals 0. And that's why here we have got two critical numbers of the function f. 3 over 2 and 0. 3 over 2 is a critical number because f prime of 3 over 2 equals 0. 0 is a critical number because f prime of 0 does not exist. Okay, so to find critical number of a given function, we saw equation f prime of x equals 0, and we find all number x so that f prime of x does not exist. Of course, x must belong to the domain of f. In our example here, the function f is well defined for any x, right? Okay, one more example. All right. So, you see, by the above definition of critical number, then you see, from the theorem 2.2, now look again. Look again this theorem. So this theorem says that if the function f had a local maximum or local minimum at c, and if f prime of c at this, then f prime of c must be 0. And that's why when we find a maximum value or minimum value of a function f in a closed interval ab, we pay our attention to critical number. And from the theorem 2.2, we got the following result. If f of c is a local maximum or a local minimum, then c must be a critical number of f. Okay, yeah. So when we find the maximum value or minimum value of a function f on a closed interval AB, then we find all critical number of the function f on the closed interval AB. Okay, and then we evaluate the value of f at critical number, the value of f at the endpoint. Compare them. The biggest number give you the maximum value, and the smallest number give you the minimum value. So here, to find the absolute maximum value, minimum value of a given function f on a closed interval AB, first we find all critical number of the function f in the open interval AB. Because if the function f maximum value or minimum value at a number c of the open interval AB, then f prime of c must be equal 0, or f prime of c does not exist. It means c must be a critical number. C must be a critical number. And then we find value of f at the endpoint. Compare them. The largest of the value from step 1 and 2 give you the absolute maximum. And the smallest number from step 1 and 2 give you the minimum value. Now we consider an example. Find the maximum value and minimum value of the function f of x given by 1 over x pi 1 minus x on the closed interval 2, 3. So first of all, we saw that the function f had a maximum value and a minimum value on the interval 2, 3. Why? Because the function f is continuous on the closed interval 2, 3. Why the function f is continuous on the closed interval 2, 3? Because the function f is just a rational function. And this rational function is well defined for any x except 0 and 1. And luckily 0 and 1 not belong to the closed interval 2, 3. That's why the function f continuous on the closed interval 2, 3. And it ensures that f had a maximum value and a minimum value on this interval. I mean absolute maximum value, absolute minimum value. All right, so now we find the maximum value, minimum value of the function f. First, we find critical number. Okay, and then we evaluate the value of f at critical number and the endpoint. Compare them. The biggest number gives you the maximum value, and the smallest number gives you the minimum value. Okay, I show you the solution. Look, first of all, the function f is continuous on the closed interval AB. And that's why the function f attains the absolute maximum value and absolute minimum value in this interval. Now, the first step, we find critical number of f. We evaluate f prime of x. Okay, it's easy, huh? Just apply Coulson rule. It gives you 2x minus 1 over x squared pi 1 minus x squared. So f prime of x equals 0. If and only if x equals 1 over 2. However, 1 over 2 does not belong to the closed interval 2, 3. And that's why we don't care this number. It's not a critical number. Because by definition, critical number must belong to the domain of f. Here we consider the function f on the domain, just closed interval 2, 3. And that's why we don't care the number 1/2. What does it mean? It means the function f has no critical number on the interval 2, 3. So we just evaluate the value of f at the endpoint. I mean, we evaluate f of 2 and f of 3. Now compare them. Okay, clearly minus 1/6 greater than minus 1/2. And that's why minus 1/6 gives you the maximum value. Minus 1/2 gives you the minimum value of the function f on the interval 2, 3. All right, one more example. Now, we find the maximum value, minimum value of the function f given by cos of x plus psi of x on the closed interval 0 to pi. So here, the function f clearly continuous everywhere because cos of x and psi of x are continuous everywhere, and that's why cos of x plus psi of x it means the function f is continuous everywhere. In particular, the function f continuous on the closed interval 0 to pi. And that's why the function f attains the maximum value, minimum value in this interval. Now, we find critical number of f. Here, you see f prime of x at this for every x. So f prime of x gives you minus psi of x plus cos of x. And now we find all number x, so that's f prime of x equals 0. And here x belongs to 0 to pi. Because we find the maximum value and minimum value of the function f on the closed interval 0 to pi. So f prime of x equals 0 gives you minus psi of x plus cos of x equals 0. Or psi of x equal cos of x, right? Okay, let me explain a little bit here. Actually, you have got like this, huh? F prime of x gives you psi of x equal cos of x, or is equivalent to tan of x equal 1. All right. You just multiply each term of the first equation by 1 over cos of x, right? Okay, and it gives you tan of x equal 1. However, maybe some student ask me the following question. Maybe cos of x equals 0. Why? Why you multiply each term of the first equation by 1 over cos of x? You know why? Because if cos of x equal 0, then you have got psi of x equals 0 too, right? If x is a solution of the equation psi of x equal cos of x, and if cos of x equals 0, then psi of x equals 0. And that's why you have got psi of x squared. X all square, huh? Plus cos of x squared equals 0, right? Here x is a solution of the equation psi of x equal cos of x. And if cos of x equals 0, it implies that psi of x equals 0. And that's why you have got psi of x squared plus cos of x equal 0. It is impossible. Because for any x, you have got cos of x squared plus psi of x squared give you 1, right? A proof by contradiction. You learn from the beginning. And that's why here, actually, it's equivalent to the equation tan of x equal 1. You see? Tan of x equal 1. Here x belong to the closed interval 0 to pi. So we have got just two solutions, pi over 2 and 5 pi over, pi over 4 and 5 pi over 4. We have got two critical numbers. Now we evaluate the value of f at critical number. We evaluate the value of f at the endpoint. It means f of 0 and f of 2 pi. Here, f of 0 give you 1, f of 2 pi give you 1. Now compare them. Square root of 2 is the biggest number, largest number. And minus square root of 2 give you the smallest number. So the maximum value of f is just f of pi over 4, square root of 2. And the minimum value of f is just minus square root of 2. So we find critical number. How? We just saw the equation f prime of x equals 0. Here x belongs to the domain of f. And we find the value of f at the critical number and at the endpoints. Compare them, you get the maximum value, minimum value. All clear, guys?
Yes, it's clear.
It's clear, huh? I think students learn it in high school already, huh? Okay, look again. This time we find the maximum value, minimum value of the function f of x given by x to the 2 over 3 on the closed interval minus 1 and 1. All right, now, first of all, you see here the function f is well defined for any x. Here we consider the function f on the closed interval minus 1 and 1. Just cube root of x squared. This function is continuous everywhere. Particularly, it continuous on the closed interval minus 1 and 1. And that's why f had a maximum value, minimum value on this interval. Okay, now we find critical number of the function f. We just saw the equation f prime of x equals 0. Here x belongs to minus 1 and 1. You see, we evaluate f prime of x. And you see f prime of x gives you now 2 over 3 and times 1 over cube root of x. So f prime of x never 0. However, this time the function f is undefined at 0. And that's why 0 is a critical number. In this example, f prime of 0 is undefined. It means f prime of 0 does not exist. And of course, 0 here belongs to the closed interval minus 1 and 1. So by definition, 0 is critical number. That's why here now we evaluate f of 0, f of -1, and f of 1. -1 and 1 here are endpoints. 0 here is a critical number. Now compare them. Clearly, the maximum value is just 1, the minimum value is just 0, right? It clear, guys?
Yes.
Bên, hô hụ bên. It's clear, bên. You absent today. Now let me check. Aha, okay. Can you hear me, Ben? Are you slept already? All right. Now we go to one of the most important theorem in this chapter. Is called the row theorem. And sometimes we call it the mean value theorem. So here, suppose that the function f is continuous on the closed interval AB and differentiable on the open interval AB. Now, differentiable on the open interval AB, what does it mean? It means the function f had a derivative at any number x of the open interval AB. I mean f prime of x at this for any x of the open interval AB. And moreover, you have got f of A equal f of B. Then this a number C. C is between A and B. So that's f prime of C equals 0. So f prime of C equals 0. What does it mean? F prime of C equals 0. It means the tangent line to the graph of f at the point C, FC, must be parallel to the x-axis. F prime of C equals 0 means the tangent line to the graph of f at the point C, f of C, must be parallel to the x-axis. Something like this. Look. Here, you see. The function f is continuous on the closed interval AB. Okay, yeah. Differentiable on the open interval AB. What does it mean? It means the tangent line to the graph of f at endpoint C, FC. Here C greater than A, less than B. It means C here belongs to the open interval AB. Then, moreover, suppose that FA equal FB. Okay. Then you see that this is a number C, so that's f prime of C equals 0. It means the tangent line to the graph of f at the point C, FC, must be parallel to the x-axis. All right? It also parallel to the horizontal line, y equal fa. Of course, equal fb too. So, look again the row theorem. The assumption of this theorem is very easy to memorize. The function f is continuous on the closed interval AB, differentiable on the open interval AB, and fa equal fb. F continuous on the closed interval AB, differentiable on the open interval AB, and fa equal fb. Then we can find a number C. CE between A and B, so thus f prime of C equals 0. Now we discuss a little bit about the proof of this theorem. You will see the proof of this theorem is very, very interesting. The proof of this theorem is very, very interesting. Now, let me show you how to prove it. Now, keep in mind that we have got two assumptions, exactly three. Huh? The first one here is f is continuous on the closed interval AB. So f is continuous on the closed interval AB, and that's why the function f attains maximum value, minimum value on the closed interval AB. This means that these two numbers, x1, x2, of the closed interval AB, so that's f of x1 is the minimum value of the function f on the closed interval AB. F of x2 is the maximum value because the function f continues on the closed interval AB. All right. Moreover, you have got the function f is differentiable on the open interval AB. Okay, forget it. We use it later. The important thing here is you have got fa equal fb. Now, we exploit this assumption. I mean, we try to use this assumption, fa equal fb. Now, we consider two different cases here. We consider two different cases here. K1, the maximum value equal the minimum value. I mean, f of x1 equal f of x2. What happened? What happened if the maximum value equal the minimum value? In
the
this
function
just constant function, right?
yes,
Constant function. Because why? Now I explain. Because you have got like this now, f of x1 less than or equal to f of x. I try to write down something. Wait. Yeah. Okay. So for any x of the closed interval AB, f of x greater than or equal to f of x1, because f of x1 is the minimum value. F of x less than or equal to f of x2, because f of x2 is the maximum value. It's clear, huh? For any x of the closed interval AB. Now we consider two different cases here. K1, f of x1 equal f of x2. In this case, you have got f of x equal f of x1 equal f of x2 for any x of the closed interval AB. In this case, you have got f of x equal f of x1 equal f of x2 for any x of the closed interval AB. What does it mean? It means f of x is just a constant function. Because the value of f of x does not change when x varies in the closed interval AB. It's just a constant function. And if f is a constant function, clearly you have got f prime of x equals 0 for any x of the open interval AB. You can choose any number c at a number x of the open interval AB, because f prime of x equals 0 for any x of the open interval AB. That's why C here is just any number of the open interval AB. Okay. Now case number 2. Case number 2 here. We assume that f of x1 less than f of x2. Okay. In this case, the function f is not a constant function. Moreover, the important thing here is FA equal FB. And that's why at least one of them, F1, F2, must belong to the open interval AB. We cannot have something like F1 equal A, F2 equal B. If F1 equal A, F2 equal B, you have got F of F1 equal F of F2. Right? Okay. Suppose that F1 equal A, F2 equal A. In this case, you have got F of F1 equal F of F2 equal F of A. Here we assume that F of F1 less than F of F2. So F of F1 less than F of F2. Moreover, FA equal FB. And that's why at least one of them, I mean F1, F2, at least one of them, or maybe both of them, just at least one of them belong to the open interval AB. So here, for example, F1 belong to the open interval AB. It means the function f attain the minimum value at a number F1 of the open interval AB by the Fermat theorem f prime of F1 equals 0. We choose the number C here, it's just F1. If F2 belongs to the open interval AB by the Fermat theorem, f prime of F2 equals 0. You see, the proof is very, very interesting. And you see, as you can see it later, this argument is used very, very often in some problem. I will give you some problem in which you use this argument. And you will see it's very, very interesting. Huh? So here you see the proof is very, very interesting and it's quite clear. Huh? We consider two different cases here. Now, in summary, the function f continued on the closed interval AB. Okay. Differentiable on the open interval AB. Moreover, FA equal FB. In this case, there exists a number C, so that f prime of C equals 0. The Rolle theorem. We can apply the Rolle theorem to many problems. Okay, I will give you some example later. Now I want to go to an extension. I want to go to an extension of the Rolle theorem. It's called the mean value theorem. Yeah, the mean value theorem. We discussed this theorem before. I give you some example. Okay, you see here, we have got almost assumption in the Rolle theorem. Here, f is continuous on the closed interval AB. Yeah. F is differentiable on the open interval AB. Yeah. This time, we done assume that FA equal FB. This is the difference between the Rolle theorem and the mean value theorem. Now, we done assume that FA equal FB. In this case, there is a number C. C is between A and B. So that f prime of C equal FB minus A over B minus A. You remember the quotient FB minus FA over B minus A? The quotient FB minus FA over B minus A give you the slope of secant line that go through A and B. Here A is the point with coordinate A at A, and B is the point with coordinate B at B. So here you see f prime equal FB minus FA over B minus A. And the quotient FB minus FA over B minus A give you the slope of secant line that go through A and B. On the other hand, f prime of C gives you the slope. Slope of what? Slope of the tangent line to the graph of f at the point C, FC. So you have got two straight lines, and they had the same slope. So what's going on? This straight line should be parallel. What does it mean? It means now we can find a number C. It also means we can find a point, let's say capital C, with coordinate CFC, so that the tangent line to the graph of f at the point CFC now parallel to the secant line that go through A and B. Here, you see, I showed you the figure. Yeah, you see here. You have got 2 points A, B. You have got the secant line go through A and B, right? Okay. And this time we can find a number C on the graph of f, so that the tangent line to the graph of f at the point CFC now parallel to the secant line AB. That this a number C, maybe that this 2, maybe that this 3, 4, 5. That this eclipse number C. And now suppose that FA equal FB. If FA equal FB, so the secant line AB is parallel to the x-axis, you get right back the Rolle theorem. If FA equal FB, so you have got the secant line that go through A and B is parallel to the x-axis, and that's why you get right back the Rolle theorem. Okay? It is called the mean value theorem. Now, how to prove it? Okay, I want to discuss the proof of this theorem. We consider the following function: g of x given by fb minus fa and tie x and minus b minus a tie f of x on the closed interval ab. Why we consider this function? It is a very, very nice question. I will explain it later. So we consider the function g defined by g of x equal fb minus fa and tie x and minus b minus a tie f of x. So the function f is continuous on the closed interval ab, differentiable on the open interval ab. And that's why the function g had the same properties. I mean, the function g is also continuous on the closed interval ab, differentiable on the open interval ab. Why? Because here you see the function g is just the sum of two functions. The first function here just fb minus fa tie x. What is this? fb minus fa is just a number. You have got the function f, you can evaluate fb, you can evaluate fa. The difference fb minus fa give you just a number. So fb minus fa tie f give you just a linear function. And linear function continuous everywhere, differentiable everywhere, right? And the second function on the right hand side of g, here it just minus b minus a tie f of x, just a constant tie f of x, and that's why this function has the same properties as the function f. That's why here the function g is continuous on the closed interval ab, differentiable on the open interval ab. It means the function g has the same properties as the function f. Moreover, you can evaluate g of a. You just replace x with a, okay? And give you fb times a minus b times f of a. You replace x with b, you have got gb. It gives the same number. You have got GA equals GB. Now we can apply the Rolle theorem to the function G. That this a number C, so that G phi of C equals 0 by the Rolle theorem. And you can evaluate G phi of X easily. Okay, just FB minus FA. Relative of X give you 1, right? And minus B minus A times F phi of X. And that's why G phi of C equals 0 give you something like this. You have got F phi of C equal FB minus FA over B minus A. Now, somehow you understand why we consider the function G. Okay? Because we try to reduce this theorem to the Rolle theorem. We consider the function G because here G phi of C equals 0 lead to F phi of C equal FB minus A over B minus A. You will see in some problem, we use this argument. Okay, I will give you some example later. So, the mean value theorem means if the function f continues on a closed interval AB, differentiable on the open interval AB, then we can find a number C on the graph of f, so that the tangent line to the graph of f at the point C, FC, is parallel to the secant line AB. And if you have got FA equal FB, the secant line AB is parallel to the x-axis, so you get right back the Rolle theorem. Okay? Okay, now I want to go back the Rolle theorem and I give you some example. Now look again the Rolle theorem. The function f is continuous on the closed interval AB, differentiable on the open interval AB, and fa equal fb. And we can find a number C between A and B, so that f prime of C equals 0. All right. So f prime of C equals 0. We can restate this conclusion at the equation f prime of x equals 0 has at least one root in the open interval AB. Right? Now let me write down something here for you. F prime of C equals 0. Here C in the open interval AB. Okay. What does it mean? It means the equation f prime of x equals 0 at least one root in the open interval AB. Right? C is just a root of the equation f prime of x equals 0. And that's why we can apply the Rolle theorem to some problem in which we have to prove equation. Here, for example, now let me see. Okay. For example, here, we consider the quadratic equation ax squared plus bx plus c equals 0. Here we assume that a is different from 0. And suppose that a, b, c satisfy the condition a over 2012 plus b over 2011 plus c over 2010 equals 0. Now we can show that the quadratic equation had at least one root in the open interval 0, 1. This example is quite interesting. However, I want to give you an easier example first. Okay. Now, wait a moment. I want to give you an easier example first. Okay. Wait a moment. I write down an example for you. Cái này cũng là cái mặt trái của cái lớp online ha. Trên lớp là thầy viết ngay luôn cái ví dụ, bây giờ thầy phải viết trên giấy. All right, just 5 minutes. Wait a moment, please. Okay. Can you see my example?
Yes.
Okay. Now look at equation 1. A0 times x to the n plus A1 times x to the n minus 1 and so on, and plus an minus 1 times x. Just a polynomial of order n. Okay? And we assume that equation 1 had a positive root x0. We assume that equation 1 had a positive root x0. X0 here is a positive number, and x0 satisfies equation 1. Now we want to solve that equation number 2. N A0 times x to the n minus 1 plus n minus 1 A1 x to the n minus 2 until an minus 1 equals 0 had a root x1 in the open interval 0x0. Okay, so the key thing here is the left hand side. Look, the left hand side of equation number 2 is just the derivative of that of equation 1. I mean, if you differentiate each term of the left hand side of equation 1, you get that of equation number 2. I mean the left hand side of equation number 2. That's why now we consider the function f given by just the left hand side of equation 1. What is this? It's just a polynomial. And polynomials is so nice. I mean, it continuous everywhere. It differentiable everywhere, right? So we consider the function f on the closed interval 0, x0. Keep in mind that x0 here is a positive root of equation 1. So the function f is continuous on the closed interval 0x0. Differentiable on the open interval 0x0. Because f is just a polynomial, it's continuous everywhere, differentiable everywhere. Moreover, you have got f of 0. Okay, you replace f with 0, you have got 0 plus 0 plus 0. All term in the left hand side of equation 1 give you just 0, right? And f of x0 give you 0 because x0 is a root of equation 1. So all assumptions of the row theorem are satisfied to the function f. I mean the function f satisfies all conditions of the row theorem. That's why that this a number c is between 0 and x0, so thus f prime of c equals 0. Because the derivative of the left hand side of equation 1 gives you the left hand side of equation number 2, and that's why the number c here is a root of equation number 2. And c is between 0 and x0. What we expected, right? We use row theorem to prove existence of solution approach of some given equation. Here is just an example. All clear, guys?
Yes, yes.
Other student? Quân, Minh Quân?
Yes.
You got it?
Yes.
Okay. Let me see. Khánh Minh, Phương Nguyên. Do you understand the solution?
Yes.
Okay. Khánh Minh?
Yes, teacher.
Gia Hân?
Yes, teacher.
All right. Okay, maybe we stop here. Next week, I will give you many examples. In which we apply the Rolle theorem, we apply Fermat theorem, and we apply the mean value theorem. Okay? All right. I feel tired right now, so I close the class session right now. Okay? Any questions, guys?
Vậy nên là mình nghỉ sớm đúng không thầy?
Đúng rồi. Bây giờ thầy mệt quá, thầy nhẹ không nổi. Sáng thầy phải đi họp nữa. Ok, we stop
Chắc tại
here.
vậy offline thầy. Chắc
Sao?
tại vì vậy online á thầy.
Nói mệt quá. Thường dạy mấy cái này dạy offline thì làm nhanh mà không khỏe quá. Okay, we stop here, huh? And next week we discuss some problem in which we apply the Rolle theorem, Fermat theorem, and mean value theorem. Okay? Any questions? All clear?
No, sir.
Okay. Goodbye, huh? And see you next week.
Thầy ơi thầy có cho em hỏi với thầy.
Rồi, ai hỏi gì hỏi đi.
Thầy ơi, tại em có gửi mail thầy, không biết thầy có nhận được mail của em chưa?
Mail gì?
Dạ mail để em hỏi cái, tại vì hồi không kiểm tra thầy, em có ghi subject, em nộp bài 4 mà em ghi lộn là subject 3 thầy. Không biết thầy có nhận được chưa? Em có nhắn lại mà thầy cũng em không thấy thầy rep lại.
Nếu có bài thì thầy chấm, chắc chắn là có chấm rồi, yên tâm đi nhá.
Dạ.
Ok. Phú Quý đúng không?
Đúng rồi thầy.
Hình như thầy có quay lại rồi nha.
Dạ. Cảm ơn thầy ạ.
Ok.
Thầy ơi,
Ai hỏi gì hỏi đi.
thầy ơi cho em hỏi là mình thi final là mình thi trước Tết hay sau Tết thầy?
Ok, thi final. Let me check. Cái lớp này là học sau mấy cái lớp kia khoảng 3 tuần đúng không ông ta? Có khả năng là thi trước Tết đó, nha. Để thầy xem lại nhé. Tuần sau đây, tuần sau thầy sẽ trả lời dứt khoát là thi trước Tết hay sau Tết nha.
Dạ.
Ok.